Gases, pressure, and temperature. We'll start with gases and temperature, then focus on pressure, and then atmospheric pressure. Gases and temperature. The gaseous state is characterized by extremely weak intermolecular forces and large distances between particles. The particles in ideal gases are far apart and not connected at all by intermolecular forces. The particles in solids are close together and locked in position by strong forces. The particles in liquids are about as close together as in solids. While not locked into position, they are held together by forces. The forces between gas particles are so weak that gas molecules are free to move and will spread throughout their container. That is not the case for liquids or solids. So here's some gas particles over here moving around in different directions, and we pull this piston up, and the gas particles will expand to fill a flexible container. We take the same container maybe and put some liquids in here, right? And they're closer together, the molecules are closer together. We pull the piston up and they stay where they are. They do not expand to fill a flexible container. A small number of gas particles, right, small number, can occupy a very large volume, resulting in very low densities. Here's a little chart on the comparison of densities of ice, water, and water vapor, all H2O but in different states. Ice has a density of 0.91 grams per milliliter. Liquid water is 0.98 grams per milliliter, pretty close. And then you have water vapor, which is the gas, 0.00052 grams per milliliter. Water vapor is over 1,800 times less dense than water. Since gases have such low densities, which means few particles in a large volume, they can be compressed into a much smaller volume. When a gas is compressed, the particles are moved much closer together, and it behaves less like an ideal gas. So here's a turbocharger that's in some cars, and that will compress the air before it enters the car or jet engine, which tends to make them more efficient and you can get more power out of them. Gases can be described by the values of these four variables: pressure, abbreviated as P, volume, V, temperature, T, and then number of moles, and that's a little n. Hopefully you're familiar with temperature, volume, and moles. Volume is measured in liters, milliliters, or cubic meters. Temperature will be measured in Celsius and Kelvin, and most of the equations require you to use Kelvin. We're going to discuss pressure a little later in this unit. This is how the three temperature scales compare to one another. Now notice we just talked about Celsius and Kelvin on the previous slide. That's because Fahrenheit is not used really in technical situations. Comparison is made by looking at the same physical phenomenon on each scale. So we have three phenomena here: the boiling point of water, the freezing point of water, and then absolute zero, where absolute zero is the lowest temperature. Kelvin has 0 K for the absolute zero, 373 Kelvin for where water boils. Celsius, water boils at 100 Celsius, and Fahrenheit is 212 degrees Fahrenheit. You can see the other comparisons there. While any of these scales can be useful, you'll be studying cases in which only the Kelvin scale can be used. Right? We said that's what all formulas are tailored for. In those cases, when given temperatures in Celsius degrees, you'll need to convert to Kelvin. We won't be using Fahrenheit degrees at all in this course, so you won't have to do that conversion. The size of the degrees in the Kelvin and degrees Celsius is the same. They are just offset by 273 degrees. Converting between these two scales is just a matter of adding or subtracting 273 degrees. So we have degrees Celsius plus 273 is equal to Kelvin. And Kelvin minus 273 is equal to degrees Celsius. And note, we don't say degrees with Kelvin, we just say Kelvin. So a temperature of 16 degrees Celsius is, we add 273 and we get 289 Kelvin. Celsius convenient for many purposes, but Kelvin has a property that makes it essential for understanding gases. For a gas, the average kinetic energy of its particles is proportional to its Kelvin temperature. This describes the average kinetic energy of the particles. Individual particles in a gas certainly have a wide range of kinetic energy. Since samples of gases usually have a very large number of particles, it is convenient and reasonable to only consider the average kinetic energy for a given sample.